Hi there, I'm Samantha Snabbs, and I'm here today at Re3D headquarters in Austin, Texas, also joined by a few of my teammates, and we're really excited about the topic today. You're all here because you signed up for the Fused Granular Fabrication User Group talk. No, while Re3D hosts it, we do manufacture a pellet printer, FGF printer. Our hope for this is just to convene people around the community. Everyone here that's attending is either interested in or is a pioneer, and we have so much to learn from each other. So regardless of the hardware and your lean, we're excited that you're here today and to get to know you. Please tell your friends. They do not have to have a gigabyte or a terabyte X. So this is one of monthly opportunities that we're trying to help support, where we meet at this time for an hour once a month, and we invite someone within the community to share an opportunity, a challenge, an insight, or where they're at in their FGF adventures. This month, we're so honored to have some true pioneers that are shaping the space and likely the impetus for a lot of attendance today. And that includes both David Kazmer as well as Stiven Kodra. And they're from the University of Massachusetts Lowell. David is the Department of Plastics Engineering at UMass Lowell, and Stiven is also within it and works alongside of him. Today, they're going to be discussing the impact of compact mixing screw extruders for improving sustainability and performance in fused granulate fabrication 3D printing with multiple polymer materials. So really excited to have them today. For context, this part of the experience is being recorded, but we'll go ahead and we'll turn that off at the end if you'd like to ask a question or connect with a number of members without that's attending today without the recording being on. So in terms of where this will live afterwards, if you want to share it with a friend, we're going to repost it to Re3D Printing's YouTube channel. We're welcome to share it with you as well, so you can reference it down the line. But with that in mind, I'll turn it over to our featured speakers for this month.
Cool. Well, thank you very much. I'm Dave Kazmer, so I'm a faculty member at UMass Lowell. My specialty is product design and machine design. And in particular, I do a lot of work in melt processing. So making plastic melts and then controlling flow and pressure, things like that. I also want to introduce Stiven Kodra, who's a doctoral student. Stiven, you want to say a few words about yourself?
Yeah, so my name is Stiven Kodra, mechanical engineering student, PhD student at UMass Lowell, working with Professor Kazmer. I've been doing a lot of research into additive, and I currently work part-time at an additive company doing inkjet, but I got started with FDM printing, so this project speaks true to me, and it's a big passion of mine.
Cool. Well, thank you. All right, let's go on to the next slide. So there's slide numbers. If people want to write down questions, we can reference the slides at the end of the talk. So I'm going to, we're going to split the talk in halves, and I'm going to talk about what I've kind of led in the last year, and then Stiven's going to talk about what he's kind of been doing the last 6 or 8 months and going forward. So first, I'm going to talk about fused granular fabrication a little bit and some just broad overview of plasticating screws. And then I'll talk about these mixing screws. And that's where Stiven and I are going to switch out. So the next slide then. All right, so FGF, we know what the strengths are, right? So we want it to be cost effective, and there's a rule of thumb in the plastics industry that anytime a person touches a pellet or a material, the price of whatever you're selling needs to double in order to just rationalize the fact that you added the value. So pellets are roughly 5 times cheaper than filament, and that's a big motivation. The material variety is also a big deal, right? There's a lot of pellets available, and the potential to add colorant and do inline compounding with FGF, if we could achieve that, would be a real game changer. Faster print speeds, a big deal, right? So typically we're looking at grams a minute on a fast, 3D printer. With FGF, right, we're looking at kilograms an hour, right? So tens or hundreds of grams per minute. And then obviously also, right, large scale printing. So the next thing though, the issues are, if you can just hit advance. Yeah, these weaknesses. So the big one is this lack of output control. And so how much volume you get out per step of the motor is kind of a big deal. We need to be able to assure what's the width and thickness of your road as you're extruding and control it well. And then with the extruder, right, we're also looking at large extruders that might have a slow response and they might drool, and all that gives us limited resolution. So what we're seeking to do is we're seeking to address these things by shrinking the size of pellet extruders, right? That's what we're about. And so this is actually very counter to the current trends in the industry. So the long-term trend in the industry over the last 30 years is to go to longer and longer screws. About 100 years ago, right, screws were on the order of 10 to 1 length to diameter ratio, and then they kind of stabilized at 20 to 1 about 20 years ago. And in the last 5, 10 years, they've just gone up to 30 to 1, even 40 to 1 length to diameter ratios. And the reason is that the longer your screw, it turns out you have more residence time. And that allows the melt to really develop, and you have more time to melt, process, and mix everything. And so you can add devolatilizing zones and all these things. The problem is, as you get longer and longer, you have more and more mass, right? Longer residence times, which actually aren't necessarily good, and your energy efficiency goes down. And so these are really unsuitable for FGF. And so what you're looking at here on the bottom, that image is actually a general purpose screw that I designed for a data standard extruder that we did a ton of characterization on. So go on to the next slide. So what you're looking at here is cross sections in the screw channels. So people think, oh yeah, extrusion, it's a nice steady process, gentle on the pellets. And that's wrong, okay? Extrusion from the point of view of the plastic pellet is brutally violent, all right? It is hard. You are putting a lot of work into forming these things and stretching them. It's really nasty. And anyway, so what we did is we did this color study with high impact polystyrene where we added black, blue, and violet pellets to a white high impact polystyrene. And you're looking on the top at the cross section of the material being processed at the 26th turn of the screw. And what I'm struck by there is you can see how poorly mixed the black is among the white hips. Even after 26 turns, you still have actually a lot of material that is not well homogenized. And that also tells me that the temperatures are not constant either in that section. And that's a big deal. Because if your temperature, as it's getting pushed off the end of the screw over on the left, you have temperature variations. That means as the material is flowing through your die and whatnot, those temperature variations are going to cause actually pressure fluctuations and volumetric flow rate fluctuations. And what that means is that your extruded is actually not going to be constant size. And in 3D printing, your road actually is going to be wobbly, essentially, different in width as you speed things up and slow things down. So there are different types of screws. Another state-of-the-art screw is this thing called the barrier screw, and we've also characterized that. And what's shocking is the image resolution isn't great. I apologize for that. You can actually see even after a mixing section, there's still these striations in the barrier screw. And so this is all pretty shocking. So that is actually a really cool reference down there, and you can go look at the reference, and we have all the sections in high res. This is like, I don't know, a lot of pixels are on this image. Anyways, let's go on to the next slide. All right, so for the last 10 years or so, I've been working on this concept of a single pellet extruder, okay? And what I mean by that is, what is the theoretical limit in terms of how long does it take to melt a pellet? And it turns out if you do the math and look at the modeling, and that's what I did in this SPE Antec 2016 paper, it should only take about 5 seconds. That's how long it should take. How long does it really take? Well, that earlier extruder I showed with the 30 to 1 L to D, it's about 15 minutes, right? And then you have to wonder, well, why is that? And so I spent the next 6, 7 years looking at multi-channel screws and then new gear pumps and had actually some real good success. but problems with the thermal temperature management down the length of these devices. And so I think now we're kind of honing in on things that really work. And so what we're trying to do here is a very direct, violent sausage grinder approach, right? Where we take these designs that are large and we really shrink them down and we make sure that the pellets are being actively worked all the time. And by doing that, we're trying to get residence times down on the order of 15 seconds. All right, so let's go on to the next slide. So we're going to now focus on these screw designs, talk about the initial concept and some modeling, and then look at the proof of concept design, and then Steven's going to pick it up. All right, so this is the first design that I designed in August of 2023, right? You can see my dating up there. And this is a 20 millimeter diameter screw that's 160 millimeters long. I just happen to have a toilet paper roll here, right? So this is about almost, this is 1.5 times the diameter of the D20. But it's, so the length would be about 1.5 times this length. So roughly this volume, but slightly different aspect ratio. At any rate, it's double flighted, and the reason it's double flighted, there's lots of reasons, but the main one is I'm sticking these mixing slots on there. And by having a mixing slot, we're going to cause the material, some of the material to go over the flight and break up the solidified bed in the next flight. And then the reason we have that double flight is the one that follows, it turns out then is going to wipe the barrel. And that function of wiping the barrel is super important, actually, for 2 reasons. One, by wiping the barrel, we never, we avoid residence time and hangups, right? We need everything to be clean. But the other thing is that the material on the barrel is basically melting by conduction. And so by doing this, we're actually getting good activity and lots of shearing between the melt in the channel and the temperature of the barrel. So that's pretty cool. So yeah, we have a very short thing. Let's see if it works, right? So let's go on to the next slide. So these are just some of the design details. So what I've tried to do is design these channels. So it's actually a thing called a variable pitch screw. And what that means is that in the feed section where the channels are deeper, the pitch is actually wider. And then as you go over to the right, where the channels are shallower, the channels are narrower. And the reason is we're maintaining a 4:1 aspect ratio, basically, of the channel width to the channel depth. And in doing that, we're going to have efficient recirculation, the melt, and we avoid kind of these long, slow, solidified beds that will tend to propagate down the screw channel. So yeah, we're all about breaking that up, okay? And then the other thing we're doing there is high compression, right? So a typical general purpose screw has a compression ratio on the order of 200%, 2:1. This is a 4:1 design, but we are relieving that compression by having these mixing slots. So as the pressure develops and there's too much stress, the pellet's going to want to go back over that flight and work on breaking up the solidified bed. So it's true, by having those mixing slots, we are going to have slightly longer residence time, but we can counteract that easily by increasing the speed of the screw. So it's not about just having so much volume per rotation of the screw, but also enabling that screw to rotate faster. So those are some of the things that so we're looking at. All right, so the next slide. So we did modeling, and Steven's done a lot of modeling too, but the modeling is very similar, our current modeling is very similar to this. So we'll just focus on this, which is published. So here we're looking at is a cross-section of the geometry, and we're just showing kind of the mesh resolution density across the screw. And so we can model something on the order of 1 million volume cells. In this case, it's a roughly 50-50 mix between fluid and solid, and it takes about 5 hours on a computer with 24 parallel threads. And what we're doing is the inlet's 140 Celsius, and the barrel is set at 240, and we're going to see kind of what is the flow rate, and temperature is a function of these different speeds. All right, yep, next slide. So This animation, right? So we're doing particle tracking here, and you can see as the material flows from the right to the left, it is warming up. And then there's these mixing slots where the hot material and the cold material will tend to intermix as you go axially down the length of the screw. So that's just kind of a visualization of how the slots are working. The next slide. So this is temperature contours of the cross-section down the length of the screw at 2 different speeds. So at 60 RPM, you get the one on the top, right? So generally, you need the material to be fully molten before it exits the screw. And so we're around 242. And the main takeaway here is that both the barrel and the screw get hotter, towards the metering zone. The faster you rotate the screw, the greater the temperature drop off is, especially in the screw and in the melt. So comparing the bottom cross section to the top cross section, you can see how the green, yellow, orange have shifted to the left. The reason it shifts to the left is that you're rotating the screw faster, and so the material in those channels doesn't have time to actually heat up as much. And so the colder material is being conveyed. And if that cold material were to reach the end of the screw, basically you could be seeing, solid pellets and very inconsistent material being extruded from your extruder. In industry, people really run these things fast and hard, and we do see those types of defects, and I've seen it as well. But not here, okay? We're still relatively slow, but things are good for us. You'll see some of the results now. All right, so what we're looking at on the top graph here is the output as a function of speed. And so the goal, right, is that in theory, the simulation predicts that we're doing something on the order of 2 kilograms an hour with this. And this is theoretical, right? We're going to look at the actuals in a minute. But yeah, the main takeaway on the modeling is that the faster you spin, the more your output increases, and it's very linear. We would love that behavior, okay? And then on the bottom, what we have is the melt temperature as a function of screw speed, and has this interesting U-shaped behavior where as you start spinning the screw faster, you actually get an increase in melt temperature because of shear heating. And then at some point, you start getting the screw going so fast that the material coming out doesn't have time to heat up. And so because of that, the material actually cools down the faster you go. So this really limits what is the operating rate of your extruder. All right, the next slide. So we did a bunch of experiments. So now we're looking at actual quantitative data. All right, so what we're doing typically is we're running high impact polystyrene and then polypropylene in this setup. We're looking at 4 different screw speeds and 2 different temperatures. And we're actually measuring the temperature of the extruder coming out, as well as the mass flow rates. And then we have some plots. So I think we have an animation coming up, or a video. Yep, hopefully it'll run. Oh, so Steven, it's not running on ours.
It's not running on mine either, yeah. Oh, hold on.
Oh.
Anything?
So can you see it on yours?
It's not moving on my end.
Oh, it's tough. Yeah. I think that might be an issue. Do I stop the share real quick and I'll start mine?
Okay.
So I'll share just this window. Hopefully you'll be able to see it. Can you see the screen here?
Yep.
Do people see this, Steven?
Yes.
Yeah, so this is this is a little setup I have here. Right, so this is a 20-to-1. And so we're actually pulling the material at a couple of feet per minute. It's going through a laser micrometer right here. So this is literally day 1. So those are the takeoffs diameters that you'll see there. And so yeah, we'll run one more time. So I think it's 13 feet a minute. So it's going pretty quick. And the diameters are on the order of 1.8. because I didn't actually expect it to work, I just used this clinchy water bath. You can see how the water bath has that brass rod there. So you have this stick slip phenomenon, which is tough, but we are extruding the high impact polystyrene in this case, if people follow that. So I'll stop my share and then you can pick that up if you want us to restart your share. So that was the very first day where we ran this thing. And we were pretty excited. And the reason I did all this was I've been working on it for 10 years. And we were entering this project with Re3D, which we're going to talk about, you know, in a few minutes in more detail, by wanting to de-risk the project, right? I didn't want to promise stuff that I didn't know we could deliver, right? So so what we have here is basically a screw pull. And the material that we ran was not only the high impact polystyrene, but also this mixed polypropylene, post-consumer polypropylene. The different colors here actually represent slightly different grades of the polypropylene. And there's also polyethylene contamination in here. So you can imagine that the materials are coming from different sources: carpet, car bumpers, you know, all these different things, right? Plastic chairs. And so what's remarkable is that by the time we come to the end here, you can see how well mixed the material is. So the melting doesn't really start until about a third down the length of the screw. And, you know, so that's all interesting and important. And then the other interesting takeaway is that this is a 20 millimeter screw. Those pellets are actually quite large, on the order of maybe 6 millimeters in diameter. And yet they process pretty well. All right, so I'll start wrapping up my part by looking at some comparative results and then hand it over to Stiven. So the next slide. All right, so what we're looking at here is comparisons of our experimental data against the simulation results that I showed earlier. And the mass output, you know, the graphs on the right are really the most important stuff. The stuff on the words on the left are just support. But the mass output generally is very linear, but we're less than what the simulation predicted. And the main reason for that is because in the simulation, we're predicting a fully dense melt channel, where in reality, in our extruder, you have this compacted bed of pellets, and there's air in there and whatnot. And so the density that's propagating forward with the screw rotation is reduced. So we're about 2/3 of the prediction, which isn't bad. Then looking at the melt temperature, what's interesting on that is that we only simulated 240 Celsius, okay? And we did 2 different experimental runs, one at 240 and one at 220. What's interesting here is that when we run 240, you can see that we're actually increasing the temperature quite a bit more than the simulation predicted. And likewise, 220, you start out slow, it's very close to 220. And as you increase the speed, the melt temperature also increases above the 220 quite a bit. The main takeaway is that this data suggests that we could run faster because we're still well above the target temperature. In our case, though, we had a 50-to-1 gearbox that really limited our speeds to 40 RPM. And so for that reason, we physically, in this setup, couldn't do that. So we didn't go above 40 RPM. All right, I think I have only maybe a couple more slides. What's interesting, looking at the laser metrology results, you can see that there's a lot of variation here down the length. Most of that is really due to the stick slip coming off that brass rod in the water bath. The main takeaway, though, is that we really were around 2 millimeters in diameter. And given the takeoff speed, this confirms that we were about 2.5 pounds an hour on this tiny little extruder, which is pretty cool. Okay, one more slide maybe. We can skip this one. So efficiencies were on the order of 50%, whereas in these large extruders, we're talking industrial scale things, they're closer to about 40%. So that's pretty cool. All right, so this is my very last slide. So what we kind of found from the preliminary work is that the mixing screw was, impressively robust. Even with this recycled polypropylene material, the energy efficiency was great. The residence times were looking good. And so where we're handing it off now is the last kind of 8 months or so, we've been working on scaling it up to the larger size. And then looking at instrumentation, and then also characterizing some stuff on residence time and how the material's melting in the screw. So Steven's going to talk about this stuff now, and then kind of what our future work is.
Yeah. Okay. So as Dr. Kazmer mentioned, we essentially took designs and learnings from this screw and applied it to a slightly larger screw. So from that 20 millimeter screw that we talked about previously, we sized up to about 31 millimeter diameter. We still kept that 8:1 L to D ratio and took a lot of learnings from the old screw design and applied it here, where here we have two feed sections or two turns that are feed sections. This allows for more constant feeding. And then again, we start that long transition zone where we're constantly increasing the compression ratio each turn of the screw. And again, also incorporating these mixing flight designs that achieve nice flow within and mixing within the variable recycled pellets that we see from the processing. Another upgrade to this larger diameter screw, to get more data, we incorporated a instrumented nozzle into this extruder, which incorporated just a pressure transducer up to 20 megapascals, as well as a melt flow thermocouple to get more accurate reading on the extruded data. So similar to the smaller screw, we ran experiments, a total of 5 replicate experiments extruding for a constant amount of time, getting samples every 60 seconds to determine the total mass flow output. This was done with varying screw speeds as well as variable barrel temperatures. So here's a video. A lot of these experiments were run in the horizontal position as shown on the left image here. And this is the extruder setup. We have 4 heater bands on there, and then you can see the instrumented nozzle with both the pressure transducer as well as the melt thermocouple in there. Then here's a video. It's a little loud, but here's a video at 75 RPM. You can see the extruder just coming out of that nozzle while we were recording some data samples.
Play it again, Sam.
Yeah. You can really see the extruded, quite stable pressures pushing that extruded mass out. Do see a little bit of die swell, but things that can be characterized. So looking at the data here, we have 3 charts. We collected 3 charts showing 3 charts for each of the experiments ran. So using that recycled polypropylene material at 220 Celsius uniform barrel temperature, all the way down in each of the sections, and running at 30 RPM. So we see at that 30 RPM, which we considered somewhat of a slower speed, we see a very nice uniform melt temperature up in the upper left-hand chart. Our set point was 220, but we can see through the shear heating that the average melt temperature is about 230 Celsius for this material. And then on that bottom left graph, we're looking at the extruded mass output over time. So we see a little bit of variability, but a consistent average of around 27 grams per minute output. Looking at the mass flow rate, you can see little error bars in there showing pretty tight data groupings. Again, maintaining that temperature of 230 Celsius, 232 Celsius, as well as the mass flow grams per minute of the 28, about 27 average. So here we have another run where we increase the screw speed to 60 RPM. As you can see, we start off at that slightly higher temperature than the set point, and then over time, we do see a slight decrease in that temperature just because the materials, as we mentioned, the residence time on this short screw is quite fast or quite small. So given that, we do see a drop off in the temperature when running constantly. A little bit more variable with the extruder mass, but this is quite common to see that drop off. So as the material is getting cool or doesn't have as much time to heat up, you're seeing more resistance in the flow rate, and therefore the extruded mass drops off a little bit. And then we looked at variable temperatures as well. So here we went to 240 degrees Celsius, again, uniform temperature across the whole barrel and screw, and then a RPM of 60. Again, we see that shear heating at the beginning quite high. So the set point was at 240. We get to about 245, and then through these continuously long, about 5 to 6 minute tests, we do see a drop off in that temperature just because of the residence time. Again, we see some variability with the extruded mass output over time, but still hovers around that 50 grams per minute set point. So with all of this experimental data, we ran some linear regression models looking at the mass output and the effect on screw speed. So this linear regression model shows a really strong correlation to the screw speed as a function of mass output. So we're seeing at about every increase of 1 RPM, we're seeing about a 0.8 gram increase in extruder output. The temperature had a little bit less of an effect, but still counted towards some of this data that we pulled from this regression model. And again, we looked at the set temperature and the screw speed, both deemed significant through this linear regression model. For every temperature C, every 1 degree Celsius increase, we see a slight increase in the extruder output. So running at higher temperatures can get us a little bit more flow rates, higher flow rates versus lower temperatures. This also highlights that when you plan on running this extruder fast in a printing application, that you could preemptively boost up the heat to compensate for, the extra flow rate that you're wanting to run at. Because this application relates to 3D printing, a lot of my experiments were done in the horizontal position, as previously shown. We wanted to make sure that we're not seeing major differences in the orientation of the screw. So I think we've all seen, if you're following pellet extrusion, you're probably seen some of these screw extruders on robot arms moving at various degrees and orientations. So in order to get a rounded data sample, we ran the screw at the horizontal position, as you saw previously, and then we ran at 45 as well as 90 degrees. Here are the results for the 45-degree angle test. This was run at our data center point of 220 degrees Celsius and 30 RPM. And again, we saw a slight increase, but nothing too significant when alternating to the 45-degree angle. Again, the 3 charts here showing the melt temperature as well as the extruder mass over time. Here is the results for the vertical test, 90 degrees, which is the most common setup that I've been seeing. Very stable at that lower speed of 30 RPM. We see very stable extruder melt temperature, and we see a little bit of variation in the extruder mass, extrudate mass, but uniform when we plot it against temperature and the mass flow rate of grams per minute. So comparing the 3 orientations, we do see a very slight increase of about 0.7 grams a minute when we're operating in the vertical position versus the horizontal position. This can be attributed to varying factors such as feeding in the channels of the screw, as well as how much pellet packing you're getting due to the orientation of the screw. So here's a screw pull we did on this larger screw. Hard to tell with this most of the material being black, but you do see mixing channels. You see a little bit of blue, and you highlight on the bottom image. You can see it being broken up by that mixing slot, and then just allowing the backflow for material to be nice and uniformly mixed. So we're about 1/3 of the way into the screw, and you can see the material's very well mixed and uniform. And as it's continuing down to the nozzle, we just get even more mixing. To highlight this even more, we ran some different material. This is a high-impact polystyrene, and we see that about that halfway point, this experiment was set up so that I ran white material at the beginning for a couple minutes, and then I threw in a mix of 10% purple into the white material and threw that batch in, and then waited about 20 seconds and then threw in another batch of material mixed with black and white. And you can see the bottom image shows the purple material backflowing almost across a full turn of the screw, again promoting that mixing, which is what we're really aiming for in the screw design. This is a video, and I put it on the lathe so you can see the full 360 view. Okay, so we've designed and operated the screw, and it's been working pretty well. We have a lot of data on it to characterize it. And then our future work, we plan on incorporating some transient controls to help integrate this better into pellet printing. So this transient control is very important, especially in 3D printing, unlike traditional single screw extrusion. During the printing process, because we're printing in 2.5D and layer by layer, we see a lot of start-stop cycles, as well as when you're doing variable printing, such as the infill versus printing walls, you sometimes will use different flow rates and different speeds. This, again, affects the extruded output. And then during startup and stopping, you see either pressure lag, oozing, or under extrusion, depending on the speeds and how you're operating this extruder or operating your printing. And this contributes to a lot of defects that a lot of people see with even traditional filament printing, but as well even more highlighted in pellet printing when we're getting into larger sizes. So with our screw, we plan on mounting it onto a tiny little desktop 3D printer, Creality CR10. This will allow us to do some transient control testing. So you see a serpentine pattern here where we plan on alternating the screw speeds and moving in certain directions faster. So in the X, we'll be limited to some by speed, but in the Y, because it's moving independently on this printer, we'll be able to operate the bed quite fast. And this printing these patterns and then characterizing the road width versus the collected data, such as the RPM and temperatures, we'll be able to characterize optimal conditions and sort of that starting and stopping behavior of the screw specifically in order to account for that. We will be using some system identification transfer functions. As mentioned, when you start the extruder, you see a pressure buildup in that top right-hand graph. And then when you stop the extruder, you see that pressure decreasing slowly. Ideally, what you want is that bottom right graph where you see the inlet mass flow. You want a nice square wave, but in reality, we can't get that because of the behavior of the fluids. So if we want to model this, we can use a transfer function shown here, where we're looking at the fluid capacitance of the polymer flow as well as the resistance and some of the inertia. And this will allow us to incorporate more finer tuned controls when operating these larger pellet printers. This is used now in, I think, most 3D printing softwares. It's called linear advanced or pressure advanced. It's a very simple model. So essentially, you can do some desktop testing to add a little correction factor to your printing. So we want to take this a little bit a step further and apply it to this pellet-based extrusion, which to our knowledge has not been done yet. Yeah. So we want to give a big thank you to Re3D for sponsoring this work, as well as the U.S. Army for the SBIR project. Big shout out to the team we're working directly with, Will, Mitchell, and Patrick, and most recently Eric. So thank you for all your continued support and collaboration on this project.
Thank you both for your time. This has been really cool to watch and listen in on. I hope it was inspiring to the other people joining today too. At this point, we do want to give time for questions. This portion is still recorded, so if you want to hold off until we turn off the recording, feel free to do so. But is anyone interested in sharing any of their thoughts or their questions with the UMass team?
I have one question.
Go for it.
Yeah, so on the topic of things that are fairly short and mix things very well, The first thing that came to mind was a mixing nozzle on those dual epoxy syringes. And as far as I know, those have two flights that go the opposite direction, if I remember correctly. I was wondering if those kind of features that point in the different direction that has the main flight could potentially facilitate some kind of mixing, or would that be something that's almost impossible to manufacture in the first place?
Yeah, so Stiven, you want me to handle that? Can you
Yeah, go
press
ahead.
21 and hit enter? So slide 21. Yeah. So a couple of things, right? One is that I actually do have some mixing breaker plates and nozzles that we've been looking at for a long time. And there's some nice publications on that if you're interested. What's interesting about the screw design is basically the entire screw is a mixer, right? And not only that, it's a kinetic mixer, it's dynamic, as opposed to a static mixer where you're going to have dead spots, right? So in any static mixer, you're going to have varying flow rates where it's low at the wall and then higher at the center line. And it's very hard to get the material to come off the wall. And so that actually limits your mixing effectiveness. And so there's different ways you can try to cut the flow. But to your very point, actually, about this dual helix, if you look at the design, it's not readily evident maybe from this, but the primary flights are clockwise, right? And then it turns out those mixing slots are actually counter-rotating at twice the pitch of the flight. So this is a 31 millimeter screw diameter. The pitch is on the flights is roughly 31. And then the slots have a pitch of roughly 16, half, going the other way, to your very point. But yeah, the main point there is that the whole screw is a mixer, and it does use the counter-rotating slots. And that's why, if you, Stiven, real quick, can you hit 34 real quick? One of the things that's remarkable about this, compared to any other screw you've seen, is that there's a clear delineation, white, pink, and black. And the pink really is only is really very localized in that transition section. This is very unusual. If you're to go back to the screw designs I've showed in the literature, you will see black, blue, and pink in a typical screw that has a 27:1 ratio. The materials actually are intermixing for maybe 10 or 12 flights. That's longer than the entirety of, so if you take a look here, right, at turn 12, you have violet, even turn 11, there's some blue there. Where going all the way to the left, you can see at turn 21, you can see how there's white and blue. It's all the way up there. And what you're looking at is the persistence of the solidified bed, which we're getting rid of with those mixing slots. So there's actually, it's all based on a lot of theory. By getting rid of the mixing slots, you are eliminating the need for heat conduction in the solidified bed. And we're relying on melt convection with the breakup of the solidified bed. And the melting rates are much, much faster, like a factor of 8 or 10 to 1. Does that answer your question?
Yeah, thank you.
That is super cool and counter to what I thought would happen. Does anyone else have any questions?
Yes,
I have a question.
I have one.
Dr.
Great.
Moshe, it's so nice to see you.
Hey, great job, Professor Kazmer, Stiven. Very interesting topic. So my question is actually 3 parts. The first part is, you said that it takes 50 seconds for one pellet to melt. And I was wondering, this is only for high impact polystyrene, or if you look on other kind of polymers family, it's different. And also let's talk about the grade. Let's say if you use 2 different grades of, let's say, PP, one that was meant for extrusion and the other one for injection molding, do they still need 50 seconds to melt, less or more? And the second question is about the grade of the material that is being used, the rheology specifically. I assume that you use like extrusion grade for this research. Why not to use, let's say, higher MFI materials and the output will grow? What is the downside of that?
All right, yeah, I'll try to hit that. So, yeah, the theoretical melting time is going to be related to the size of your pellet, right? And so, yeah, the bigger your pellet, the longer it's going to take. But there's rules of thumb, and the 2016 Amtech paper does have kind of a derivation in there where it plots that. And you're assuming some kind of heat transfer coefficient on the outside of your pellet. You are correct that it will be dependent on the temperature and the melting temperature of your material. But the trick is that most material suppliers have to design their materials to behave in some expected way. And because of that, there's basically some dimensionless ratios you can use to understand, yeah, it's going to be pretty similar from one case to the next. And by that, we're really interested in order of magnitude. It's going to vary by plus or minus 20, 30%, but that's close enough. So having said that, in terms of the MFR question, melt flow index question, these materials that we're using are on the order of an 8 MFI. So they're not really super low, right? They're kind of mid-range. And we haven't seen a lot of variability. The HIPS is a little more viscous than the polyethylene or polypropylene once it's molten. But from one material to another, we've now tested maybe 3 different materials between Stiven and my other work. So it's pretty robust, which is interesting. One of the things, and then addressing your question about molding and times, yeah, I mean, I look at this. So different providers, I'm not going to use names due to confidentiality, but manufacturers have asked me to, oh, could you design us these extruders? We're tired of these big expensive extruders. Can you design smaller ones? And I'm always tentative, right? Because these people are putting out hundreds of millions of dollars of product, in their plants per year on these extruders. And yeah, you don't want to tarnish the reputation. But I think we're now at the point where, yeah, I think it's good. A question is, can we eliminate the reciprocating screw in molding? And there's actually a lot of reasons from the point of view of machine design and material consistency, if we could do that. But that might be another project down the road.
Thank you.
I believe Alan has a question as well.
Yeah, no, thank you for the presentation. Super, super cool work. My question is really if you guys were able to compare those pressure readings with and without that thermocouple, just because it looks like it protrudes inside of the capillary, which can cause some local disturbances and will fluctuate those pressure readings. And if so, like, did that kind of change your model predictions for your extrusion simulations?
Yeah, Stiven, why don't you go to slide 22 and you cover this one?
Sure. Yeah, so we did not run it with and without the melt temperature in there. I don't think we'd see much differences, but that is an interesting point and maybe something we could look at down the road. But considering how important we found the melt temperature to be, we didn't really consider running it without that in there. I don't predict any major differences, but in terms of I don't think so, but I think it'd be interesting to run it to see if we do see anything. I don't know if Professor Kazmer has anything else to say, but
yeah, I'll pile on. So one thing is the melt temperature, the intrusive tip. You actually want to go as far into the melt as you can because you want to reduce the amount of heat conduction being lost to the steel around it. And frankly, I think our signal to noise ratio is pretty good. One of the frustrations I have in 3D printing in general is the lack of instrumentation. And I've had former students, so Austin Colin, who I saw in Austin on, he might actually be here. And then also another former student, Tim Coogan. We've all looked at pressure sensing in regular 3D printing. And this is, in a way, is an extension of that work. So I want to give kudos to that. But certainly, I mean, the pressure, when you see the pressure, it really does vary a lot from one moment to the next. And the flow rates really are varying. And if you're not making adjustments, then your control is limited.
No, I think that's super cool because I've done some instrumentation on extruders, and like you said, that pressure reading just fluctuates a lot, and depending on how much is filled, how much is not filled, and so it'd be interesting to use like all that data to kind of predict those pressure readings using like data-driven modeling as well. But I guess my second question would be, how did you guys characterize that residence time distribution? Was it by those screw pullouts or some camera-based system?
Yeah, so we did the screw pulls essentially in between those color loadings. I timed it, so essentially every 20 seconds is when I would put in that colored batch of material, and then once we did the screw pull, we were able to determine, after I stopped the screw, how many minutes had passed or seconds really, and how far along the screw the material had gotten.
Yeah, so a couple quick things I wanted to add, and then I'll extend on that last one. Our pressure sensing, we're collecting data at 20 kilohertz. And so that it's just too much data right now, actually. And so we're trying to work on getting the acquisition on that synchronized well with the temperature data, and that's why we didn't show that data. But we do have working pressure sensing. On Stiven, he said, okay, yeah, we add 10 grams every 20 seconds, and that's at 30 RPM, right? So literally, if you're to throw in the 10 grams of material and let the extruder run at 60 RPM, you'd be done with it with 10 turns of the screw. Meaning that it flows and then it stops. Okay, so that tells us actually the residence time in typical extrusion is a long bell curve, where this is more like a sharp, almost more uniform distribution. I'm not going to say it's uniform, but the transitions are very very fast. And so yeah, there is a potential for inline color compounding and doing some interesting things with that. But again, that's kind of out of scope for what we're doing. And we didn't mention it except for at the very end, right? But Re3D has a project where we're trying to reuse waste materials from the US Army and print useful products from that. And so, this extruder that we're showing today is being integrated with some of those systems, and we'll continue to work on that integration.
Awesome. No, thank you for the presentation and for answering the questions.
Thank you. Does anyone else have any questions? Awesome. Well, we'll go ahead and turn the recording off, but before we do, if you're interested in speaking and presenting your work, please reach out to our team. You can find us on social, or you can reach us at info@re3d.org, myself, Samantha, at re3d.org. But we're going to go ahead and turn off the recording. We hope you come back next month. Again, this will be hosted on our YouTube channel. Michael, do you mind turning it off?